Good afternoon, everybody. And one of the challenges in this talk was to try to, the whole conference was to try to make bridges between different areas and try to make it as interdisciplinary as possible. So here I'll try to accomplish the connection between a subject which is a classic of strongly correlated system, which is Mott insulators and Mott transitions, with some bio-inspired subjects just as synaptic behavior. But as you know, the conference also had a topic on ASD CFT, and I found a very hard time finding a connection between this and that, but that was fantastically solved in the talk that we hear about from Takeshi Oka before. So I think that all the connections, at least we got the connectivity between all the subjects right. Okay, so I'd like to start by acknowledging my collaborators, especially the group of these three gentlemen from Nantes in France, which are mostly responsible for launching this experimental investigation that I'm going to describe. Also, my colleagues in Buenos Aires, who were done some experiments and some theoretical calculations that I'll show you later, and most especially, my former postdoc, Pablo Stoliar, who is now in Nanogune, and since this workshop is about bad metals, I thought I should pick up this picture from him, who looks like a bad guy, but actually he's a very nice person, and there you have a more reasonable one. Okay, so the work that I'm going to describe, the main part of it is contained in these recent references. Okay, so we're going to be talking about the destruction of Mott insulators. So first question is, what is a Mott transition? Of course, we heard a lot about that, and many people here are experts in the field. Mott transition prime example is found in V203, and basically it is a system, a compound, where naively you just do the electronic counting and you expect it to be a metal. You are less naive, you do a state-of-the-art density functional calculation, and it's still a metal. But you go to the lab, do the experiment, and when you get a good sample, it's an insulator. So this is the case in V203, where here you expect a metal, but it is an insulator. And I want to make clear that it's not this insulator, which is antiferromagnetic insulator. The Mott insulator is an insulator. We really do not expect it to be an insulator because there is no long-range order. In the presence of long-range order, of course, you can change the bands and change the lattice periodicity and get insulators. But here you have a paramagnetic insulator. Moreover, as it was emphasized before, you can go from this insulating state to this metallic state, above in temperature, changing the pressure, in a very continuous fashion, in a totally continuous fashion, and you have a first-order line that ends in a second-order critical point, like in the water-vapor transition. So from a theoretical point of view, of course, there's no questions. Our spherical cow model is the Hubbard model, which has two bands. It's very simple. It has two terms, one kinetic energy term here, a tight binding Hamiltonian with nearest neighbor coping, and then you have a correlation term. If you cross out that one, you'd consider the limit where you only have a conduction band. You fill it, you put 1 electron per side, you expect a metal, and of course you get a metal with a bandwidth of the order of the hopping T. On the other extreme case, when there is no T, you just have an atomic Hamiltonian. And if you put 1 particle per side, you have a fully occupied flat band with a charge gap of the order of U. So you see that at least the two limits of this thing is OK. So you have a metal and an insulator. Now, to solve this deceptively simple model in 1D, the moment you put a finite U, immediately it opens a gap. So clearly, that cannot be the experimental situation where you have a metal insulator transition. So it has to happen at intermediate values. U, of course, is always maybe very small, but it's not negligible. It's just the Coulomb repulsion. It has some value in 1D. We cannot solve that. 2D, of course, is the holy grail of condensed matter physics for the past 30, strongly correlated condensed matter physics for the past 30 years. So the advances in our understanding was achieved in the 90s by the development of dynamical mean field theory. So this is by now some classic image that we have of how the Mott transition occurs as a function of u over the bandwidth when you consider the limit of large lattice connectivity, large dimensionality, or the same thing which goes by the name of DMFT, dynamical mean field theory. So there you have the weak coupling limit with a small value of u, and what you see is that this metallic band is just slightly distorted by the emergence of some spectral wave that is being pushed at higher energies. As you crank up u, you see that this thing is really emerging as two wings, the lower and upper Hubbard band that start gathering much of the spectral weight. If you keep on going, you'll find an intermediate value of u, a critical value of u, where this quasi-particle peak becomes very, very narrow, and all the weight is already in the Hubbard bands, and beyond that, you open a gap, and you have your Mott insulator. A very surprising thing that happened was that if you start from the insulating side, and you start lowering the value of u and following this solution, what you find out is that for these same values of parameters, you can still have an insulating solution with the two Hubbard bands just getting closer and closer. And that goes on until the two bands touch and you destroy your insulator. So there is a region there in parameter space for a half-field system, which is where there are coexistent solutions, pretty much as in the Ising model, where at low temperature you have the two ferromagnetic solutions. So if you put that in a phase diagram, these calculations correspond to the t equal to 0. This is interaction in units of the bandwidth. And what I was mentioning before is that at low u, you have a paramagnetic metal. In cranking up u, you destroy it at that value, which we call UC2. And if you, beyond that, you have an insulator. And when you go back from the insulator, lower in u, you find this region of coexistence, and here you destroy your insulator. When you go up in temperature, of course, these two solutions do not vanish in thin air. They give place to a coexistent region. If the temperature is high enough, of course, everything becomes continuous. There are no really distinctions at high temperature between metals and insulators. Everything conducts. So at high temperature, you have a bunch of crossovers. That was the topic of the beautiful talk that we hear from Vlad the first day. Okay, since here you have a region of coexistence, you have to compare the free energy in order to decide which is the true solution of the model, and that gives place to a first order line. So when you put back that in a model with some frustration, finite frustration, you can find all the same topology as in the V203 that I was mentioning a moment ago, where this first order line occurs there, ends in a second order critical point. Above that, you have crossovers, and at low temperature, you have different antiferromagnetic states. So you have a correlated metal and an insulator, and an important thing is that this correlated metal, you can destroy it by heating. So this is the V203 phase diagram, which corresponds to the previous one. And this has been always the classic example of a Mott transition in a Mott insulator. But however, this has also been matter of ongoing debate on and on and on. And this is only the last one who questions the validity of a Mott-Hubbard approach for V203 for a variety of issues that I'm not going to discuss now. What I'm going to do now is just present another compound that probably you do not know or hear about, as it's not as famous yet as V203, which actually belongs to a family of compounds which are tailor-made 3D Mott insulators. So this is a system which is as good as you can dream of. So it looks like awfully complicated, but it's quite simple. So you have to forget about the gallium or the germanium, which is the red octahedra here. Forget about them. Here you have some also in yellow, the sulfur or selenium that you can also forget about them. And the only thing to retain is just the blue octahedra, which are made of a transition metal oxide, which could be vanadium, niobium, tantalum, molybdenum, a variety. And all these families all are Mott insulators. Many of them do not order in any way, do not have any structural transition, so you can go to very, very low temperatures. So why these systems are so nice? Because all the transition metal oxides form a very compact cluster. The distance between the transition metal atoms here is only 3 atoms, and the distance between clusters is over 4 atoms. So the proper treatment is to consider this as molecular small molecules and have molecular orbitals and start filling up those molecular orbitals. If you do the electronic counting, you find out that you're going to get 1 remaining electron per tetrahedron. And then the hopping between these tetrahedron is very small because they are far. Moreover, all this thing is an FCC lattice. All the blue tetrahedron form an FCC lattice, full of these triangles. So that fully frustrates the system, and the system doesn't want to order. So since this does not want to order, this thing will not have a strong tendency to antiferromagnetism. So as I said, you have your molecular orbitals, you put your electrons, and you find out that you have 1 remaining electron in a T2G band because has a cubic lattice, it's an FCC. So you have T2G bands being the conduction bands there with 1 remaining electron. You would expect to have a partially filled band, therefore a metal. But in real life, these systems are insulators with a gap of a fraction of the electron volt. And this has been the investigation of this group in 2005. Before that, there is a PRL by this group, I think it's at MIT, where you see that this system, one of these members of the family, the GTS, indeed has a very high growth of the resistivity of an insulator. So this is a Mott insulator. But one of the hallmarks of Mott transitions is that you change the U over W ratio, and you can have a transition. Okay? Can go into a metallic state. So this is pressure experiments, and you crank up the pressure, and what you see is, in fact, that you go from an insulator to a metallic state. Moreover, for the superconductivity aficionados, at 4 Kelvin, below 4 Kelvin, this system goes into a superconducting state. So you see that you can change orders of magnitude the resistivity and have this change from an insulator to a metal. It's very little known what they have at low temperature, but I'm not sure there are good experiments, magnetic experiments, but I'm not totally sure about that. Okay, so after this, a very interesting discovery was made by the group in Nantes, where they start with one of these compounds, which looked insulating, and then applying a strong electric pulse, managed to change the resistance orders of magnitude. Moreover, they found that the change was non-volatile. They apply a strong pulse, the resistance changed, and then it remained, you see, almost 3 orders of magnitude lower than the initial value. Moreover, if you apply a reverse field, you can undo this effect. So immediately you think of applications. So this can be applied as a non-volatile memory, and the switching time can be as low as to be in the nanoscale regime. So now, since we are DMFT people, we look at this and I said, is this oversold? I mean, is this really a Mott-Hubbard system? I have just tried to convince you that it's as good a Mott insulating system as it could be. There is no antiferromagnetism. It's 3D. It has an FCC structure, so it's fully frustrated with high connectivity, because the FCC lattice has a connectivity of 12, I think. So you're just like, this is why I think these systems are like dream systems to test the dynamical mean field theory predictions. And now, of course, I look at that with a lot of care, and I see there are some stuff that I don't like. The stuff that I don't like is that as a function of pressure, this thing continuously goes into the metal. So this doesn't show any sign of hysteresis, which is one of the hallmark of V2O3 and what made DMFT so popular. On the other hand, close to the transition, where you go from insulator to metal, there should be this non-monotonic behavior that has been predicted and validated in organics or even V2O3, very close to the transition. You see that the system is, when you're just in the correlated metallic state, when you come from high temperature, the system thinks that it's an insulator, but suddenly you hit the onset of coherence when the quasiparticles are formed, and immediately you go down to a very nice Fermi-liquid state. So neither the coexistence region with the hysteresis nor this non-monotonic behavior was observed in these samples. So with this, we said, well, let's try to do theory best as we can. And as I said, this system is so nice that also from the band structure calculation point of view, it's very nice to do a LDA plus DMFT calculation. Why? Because this is the LDA bands. And as you see, the 3 T2G bands that I mentioned as the important one with the one remaining electron per tetrahedra are there and are well separated from the rest of the valence band and from the rest of the upper empty bands. So this thing is well separated. We see it there in the density of states. So you can just focus onto that and do a DMFT calculation on this manifold, which is well separated. So it's a very nice system. So to do that, you have to do a Vanier, you construct the Vanier orbitals. With that, your tight binding Hamiltonian. With the tight binding Hamiltonian, you can do the LDA plus the DMFT, computing the correlation corrections to the band structure. This is just a vision of the orbitals. So these are the T2G localized orbitals, where you see this is viewed from the top, from the side, and from the other side. You see that this is totally analogous to the T2G bands, the XY, YZ, and ZX that we're familiar in perovskites. So it's totally analogous. They look weird, but it's pretty much the same. So, of course, one of the problems with the LDA plus DMFT calculations is that we do not know reliably how to compute U. So then we put some physical input, and we know that applying a pressure to this system, we manage to get into a metallic state. So clearly, the U has to be such that places the system next to the Mott point. So what we done was start scanning through the values of U, considering U as a parameter, and see when we open the gap. And when we open the gap, we said, well, U has to be right there. So you see, this is, so we fixed, of course, in the experiment, you do something a bit different. You fix the value of U, and you change the bandwidth. But since the changes are small, it is just more practical to have one band structure calculation and then use U as a parameter. So this is what we've done. We fix the band structure, and we use U as the parameter. So if U is 9, this is the N versus mu. So the slope here at 1 is the compressibility. So this is a compressible state. It's metallic. Then the compressibility starts increasing, and then you get a plateau. When you get a plateau, you have an incompressible state, which is the indication of the presence of a Mott insulator. You change your chemical potential, and you cannot dope more electrons to the system. So you see, but the time you hit 1.3, you have a well-developed plateau, therefore a Mott gap. So we fix U to be 1.2, the blue line there. And with that, we said, well, can we predict, put a number on what is the hysteresis that this system should have? So this is done here. So this is for different temperatures. These are the coexistence of solutions that you get on this range of values. So U 1.2 would be over there. So you see that there are hysteresis regimes at low temperature. And as you go to high temperature, the hysteresis becomes very small. So the black curve is 230 Kelvin, and above that, the hysteresis just becomes experimentally irrelevant. So this is our prediction to the coexistence regime. And moreover, with these values of U, we can get the interacting band structure, the Mott gap is open there, and we can get all the gaps, the transport gap, delta, and the optical gap there, and that fit very nicely with available transport and optical conductivity experiments. So with all this, I try to convince an experimental friend that he has to be a friend, because otherwise he will never convince somebody to do a pressure experiment on crystals, on single crystals that were fabricated in Nantes. I brought to Argentina, so these guys at UVA, and they gave me the crystals in a small plastic transparent box. And when I got the box, I said, but listen, you forgot to put the crystals in. I said, no, 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 you look in the little circle there. So there were just, pieces of dust. These things are 100 of microns or something like that. These are the size of the crystals. On these crystals, you have to put 6 electrodes and then put it in this diamond anvil and crank it up to several gigapascals. So this experiment is not so simple, and then, of course, can with temperature and everything. And after 6 months, my colleague have found this beautiful set of data where you see that at low pressure, there you see the activated behavior. This is the Mott insulator. At very high pressure of 5 gigapascal, you have here the non-monotonic behavior. So this really, if you just forget about that part, only the high temperature part looks very nicely as what Vlad showed us. But the most exciting thing is that in between the insulator and the metal, you have here a huge hysteresis regime, and this hysteresis regime extended to about 100 Kelvin, which is not so bad from our prediction. So I remind you, this theory has ingredients which are in the scale of the electron volts. It's 10 to the 4 Kelvin, and we are making a prediction 2 orders of magnitude below with a very simple LDA plus DMFT calculation. So the fact that this thing extended to 100 Kelvin is not so bad. This should depend a little bit on the pressure. It's impossible to do fine-tuning of this. It was a miracle that he got that. But since I was worried it could have been a miracle he got that, I said, you have to repeat this thing and get a double check that this is not an accident. So he went for another 6 months and got this other data, where you see this is a different sample, this is a different pressure, and again, you see the hysteresis and the very nice data, which are qualitatively very similar to this. So moreover, when he got into this hysteresis regime, he did something very smart, which was, there to lower the current. So he got into this metallic state and then increased the current again. And by increasing the current, you locally heat. When you locally heat, the system jumps in resistivity. This is destroying the quasi-particle peak. This is evidence of, or consistent with destroying the quasi-particle peak and going nowhere, anywhere, but just on the insulating branch. And then once in the insulating branch, you can go down and then lower the current again, lowering the local heating, so the system jumps back again to the metallic branch. So you see that you have really B-stability between two well-defined states. So when you compare this thing with the previous data, the key is that now we have single crystals. So this thing has been done in powder, so that's why the behavior was not proper. But then I show you how just believing firmly that the dynamic amenity theory calculation had a lot of sense. We just made a much better connection.
Putting the current, you're actually putting the latent heat, right?
Yes, that's right.
Can one estimate from the current pulse how much latent heat does he need, and how that, because you can also, the theory can also tell you that.
Yeah, we should do that, but it's not so easy to do the estimations for the heat transport coefficients. So it's not so easy. But okay, so did all the tests possible with the different, the experimentalists did all the tests possible with different crystals and different electrodes, and everything worked very fine. Okay, so that is it. We have a very nice canonical Mott-Hubbard system, experimental, that agrees with the theory, and that is very fine. Okay, so now comes the challenge of trying to build bridges between Mott physics, classic Mott physics, and neuromorphic behavior. So this is combining Mott physics with electronics, which goes by the name of Motronics. This is an idea pushed among the originators of the Motronics is Isao Inoue. And here, the flavor of this Motronic application is we want to apply electric fields to the Mott insulators to see how they behave and if they can be useful for some applications. So one warning is not to mix up what I'm talking about with the Mott transition in VO2. So VO2 is always also quoted as an example of a Mott transition. This is of a different flavor. There, your low temperature state is an insulator, and Ivan showed us that it's most likely that it's temperature which can trigger the transition from an insulator to the metal. This data there. There are groups which are not totally happy with that vision, and they propose that it's electronic driven. In any case, I think I'm quite in agreement with what Ivan told us about, but I want to emphasize here that we're going to be considering an insulator which is there. So by applying an electric field to that, we can only move here. So at higher temperature, by heating, you're never going to get to a metal. So here, you heat, you have a transition, a dramatic transition to a metal. Here, there is no dramatic transition to a metal. And if you cool, you would go to another insulator. So that's not the same situation here. It's qualitatively different. Okay, so we go back to this GTS, this beautiful Mott system, and the early investigations of the group in Nantes show that there is non-volatile resistive change. You see you have a system which is in a high resistive state. This is current, this is voltage, and then by a strong voltage, you can switch it to a more conductive branch, so you have this new IV, but this can be undone and go back to this thing, so you have the non-volatility that I mentioned before. So this means, this is what I showed you before, is you apply a very strong field, a very strong electric pulse, and you can change the initial resistance very quickly to a value that remains low. So this is a non-volatile change. If your pulse is very small, of course, you do nothing to the system. You start with high resistance, and you remain with high resistance. Now, one problem that is in there is that this state, we do not have a lot of control how to undo this. So if you apply the negative voltage pulse, you sort of go back to a high temperature, a high resistance state, but not quite the same value. And sometimes you can do that with positive voltage, sometimes with negative voltage. So this thing is not totally, of course, the situation is reproducible, but not point by point. On the other hand, when you do the systematic study, you find out that when the voltage is not so high and not so low, there is a regime in the middle where you have this resistive transition, but it is volatile. That is, when your pulse is terminated, the system comes back to the original value. And this effect here is perfectly reproducible. You can do this 10,000 times, and you'll get point-by-point reproduction of this behavior. So this is intrinsic behavior, and one way to think about that, you can think of this as being like in an elastic regime. So this would be an elastic regime, like a spring. It comes back exactly to the same situation, but this is more plastic. So it's like you have a paper clip that you can just wind when you're bored, and then you unwind, and it almost gets back to the same situation and almost work, but it's not quite the same. So there you are introducing defects or whatever. In any case, this is plastic, and this is elastic, and very well reproducible. Okay, so you do this now in a systematic fashion, and you apply voltage pulses of different intensities. So here you have voltage, and you see that the transition occurs faster and faster as the voltage is increased. So when you put this voltage versus current on this plot, you see that this is the initial branch, the high resistant branch. So you apply a voltage pulse of this magnitude, and after a little while, the system back changes to the other branch. So the changing from this low current to high current is this transition from this high voltage to the low voltage on the sample. So this is the voltage on the sample. This is the voltage on the sample. So you see that when there is a transition, the current shoots up, and the voltage becomes pretty much regulated. And so this is very fast. This is getting lower, slower, slower, and here is the limit of very small voltage above the threshold field. So this takes longer and longer to get the transition. So this indicated a very well-defined threshold magnitude for the field, which is of the order of the kilovolt per centimeter. Very well. So one immediate question is this thing intrinsic of Mott insulators, or is just peculiar to the GTS system? So the idea was to go and look for the classic examples of Mott Hubbard systems that we know, V2O3 that I mentioned before, and nickel sulfur selenide that was also mentioned in the talk the first day. So these two systems has this specific first order line in which you can melt a metal into an insulator. You heat up this metal, this is a correlated metal, and it becomes an insulator, presumably destroying quasi-particle peak. This first order line ends in a high temperature second order critical point, and here the same thing, you have correlated metal and the first order line tilted that way. So the experimental group in Nantes, this systematic study in these three systems, and all show an amazingly similar behavior. So here is the data that I showed you before with this series of voltage versus time transitions. This is in V2O3. Actually, it's not V2O3. V2O3 is metallic. You have to put some chrome in order to make it insulator. So this is chrome. Same thing for nickel sulfur selenide. And you see that this qualitatively resembles the same. So it's amazing universal behavior. Moreover, if you look at the threshold fields above which you start getting a transition, you see that all are in the kilovolt per centimeter regime, and the times involved are of the order of the microseconds. And of course, with higher voltage, you can make it quicker. Okay, so what is the origin of this universal behavior? That's the question we're asking. So what is the origin of Mott electric breakdown? So we heard much of this in the talk of Takeshi Oka. Here I'm just showing a cartoon of this. You have the lower Hubbard band and the upper Hubbard band. This is full, this is empty. So the idea is that you tilt these bands applying an electric field. So this is the Mott gap. This is the delocalization of the doublons. These are virtual excitations in which particles sites can become doubly occupied. But of course, since this system is an insulator, this electron cannot go very far within a length scale of the order of epsilon. It just comes back. So in order to destroy this insulator, to delocalize these doublons, what you have to do is to tilt this band enough, delta over eta, so that within the eta, this doublon can get into the empty Hubbard band and then be free to move. And there you sort of destroy your... As I said, in 1D, everything can be done. So all this cartoon can be put on firm footing. And there, the threshold field, which is expected to go as the Mott gap divided by eta, the threshold field goes as delta square. 1 over eta goes like delta Mott. So you expect if you put numbers to that, you expect a threshold field, which would be delta is of the order of a fraction of the electron volt. Eta is conservative of a nanometer. It's already pretty large. So you see that the threshold fields that you may expect are megavolt per centimeter. However, in the experiments, this is kilovolt per centimeter. And the times involved for this, as we heard also from Takeshi Oka, should be related by the uncertainty principle, so should be times which are very, very short. And here I was mentioning that microseconds can be needed in order to see the transition. So, okay. So, of course, ideally one would try to get a Mott-Hubbard system and analyze that out of equilibrium. 1D is no good, so we have to go to DMFT. So 1D work was pioneering work also of Takeshi Oka during this series of papers. He also has fruitful collaborations in trying to put DMFT out of equilibrium, but the problem is extremely hard. You have to do a full many-body problem with the coexistence and everything out of equilibrium for long sufficient times, and these qualitative considerations may already tell you that even that will not be enough. So some more ingredients have to be present. So since I cannot do DMFT out of equilibrium and on top of that, guess what is missing? My attitude now will be just very, very humble. I will just model phenomenologically the Mott transition, but not just with a capricious manner. I will try to take advantage of the knowledge from DMFT. So this is the physics we are after. We want to capture this transition and also a little bit of at least qualitative of the dynamics. So we built a resistor network, and a resistor network that resembles the experimental system. So this is the sample. There's a load resistance, which is there, and the applied voltage is there. So there are resistor networks of all sizes and shapes. Everything is defined by your assumptions for the resistance. So our assumptions is that we have two states, that the lower state, the most stable state, is a Mott insulator, which has high resistance and is more stable. And beyond an energetic barrier, you can access a metastable state, which is a correlated metal. But since this is metastable, it has a higher energy, and of course has a barrier to relax back to the Mott insulating state. So the additional assumption we made is that on these cells, when you are in the insulating state, you will have some voltage drop, some local voltage drop, and that the probability of going beyond this barrier can be increased by lowering the barrier with the applied voltage. So we start with a fully resistive lattice. We solve the Kirchhoff equations for our voltage protocol. We have the voltage drop at each cell. We compute the probability of going from the insulator to the metal. After each time step, we have a new lattice, with a lattice of resistors. We solve for that lattice all the voltages, and we compute the new probabilities, and we keep on doing that over and over through the length of our paths. Clearly, it is embedded here that this system is volatile, because when there is no more paths, all these things will relax back to the Mott insulating state. So this is what we wanted to capture, and this is the results of the simulations. So you see that you apply the voltage, you have a very well-defined threshold beyond which there is a transition. Being that is nothing, and when you see systematic behavior of this, you increase the voltage over the threshold, the limits of the threshold, and you see that the transition goes faster and faster. So this is a linear scale, and this is a log scale that lets you see that this thing really is very rapidly increasing. So since this is simulation, we can ask about all the details how this thing happens. So this is a resistor network. All the white spots are insulating states, and this is our starting state. The color coding here will be the applied voltage. So you see that since all the lattice initially is homogeneously insulated, the applied voltage between the bottom and the top. And you're going to see that these sides go metallic, and at the same time, the voltage drops in the whole system, the local electric fields are computed, and you'll see that blue is less electric field, and yellow and red is stronger electric field. If the electric field is stronger, then the probability of changing into the metallic, just destroying the insulator, will be faster. So this is what I just mentioned in pictures. So you see that you get some states going metallic, you get some states going metallic, but suddenly you have a nucleation of a little segment. That little segment produces a very strong field in the head and make this atoms. So in order to see this clearly, these are snapshots of what you just seen. So I showed that at some point you have a good probability to form a segment. The moment you form a segment, you see that you have blue now low field because these two cells are metallic. So now you have this metallic filament. The voltage drop has to be the rest of the system. So the electric field is enhanced at the tip of this filament. So that makes the filament grow very fast, as you see a moment ago. And you see that the field is firmly enhanced at the tip. So this makes that now the thing branches out, and you have a filament that grows, becomes thicker and thicker. So this thing grows and gets to the other side. Once it gets to the other side, all this region is a nice metallic region. So then the filament realizes that its state is not so conducting, so it reverses the direction and breaks all this part, and then this thing relaxes further until you get a more or less homogeneous filament. You switch off the voltage, and this thing goes away. So you can do this beneath the threshold. If you do that beneath the threshold, you see that some points go metallic, but before any segment can be formed, this thing kills itself. So in this case, it's like walking in Paris a typical day where it drizzles, but it doesn't rain at all. So people do not use an umbrella anymore. You just go out, and you don't get soaked because your body just heats up and you get dry at the same time. You get wet by the drizzle and you never get drenched. On the other hand, when you go to Buenos Aires, you better pick an umbrella because there, when it rains, and then you don't have enough time to get dry up, you get totally soaked. So you see here, you get soaked, and if one filament is not enough to lower the resistance of the system, the voltage drop on the whole system beneath the threshold, of course you will have further breakdowns. So you have more filaments, and the resistance of the system will keep on going down. The voltage of the sample will keep on going down, and it will go down until it reaches the threshold. And then it will not go down anymore. So that's how you can understand the existence of this very, very nice threshold. And moreover, higher voltage, you have more filaments, so that allows you to understand in the context of resistive switching why higher compliance current will give you lower resistance, but that is for resistive switching aficionados. Okay, so this gets me to the final point of this story, which is this very unexpected behavior. And why I think this is important? Because, well, we had a resistive switching, I present a resistor network, and I said, well, I can also hook up a resistor network that will do something similar to that. So a theory or a model is only really worthwhile if it can make a prediction. So if this assumption here, which was the key assumption of the resistor network, is valid, it involves the existence of a new time state, which is the relaxation from this metastable metallic state back to the Mott insulator. So now you can imagine if there is a new time, relaxation time involved there, you can consider the following experiment. So let's apply a pulse, which is shorter, a pulse with a given voltage, which is shorter than the time you need in order to get the transition. So one short pulse is not enough. So you apply a short pulse, of course you don't get the transition, and now you wait until you repeat the pulse. Now when you wait, there are two possibilities. You wait beyond that relaxation time or beneath that relaxation time. if you wait too long, of course the system will fill back. If it fills back, then you will not be able to, with another short pulse, get the system to have the transition. So you can apply as many pulses as you want, but if they are too far apart one from the other, the system will not have a transition. On the other hand, if you are beneath this time threshold, you will have a transition, and of course, the shorter the time between the pulses, your damage has less time to get healed, so you can accumulate pulses faster, so the smallest number of pulses will be when this time goes down to 0, the time between pulses. So you could do that in the simulation. This is a parameter such that you have 1, 2, 3, 4, and in the 5th pulse, you have a transition. Once you have the transition, the system remains there. It doesn't have enough time to relax back. You just, every time it wants to come back, you change it on. So you do that systematically, you study that systematically as a function of time, of the time between the pulses, and you have this phase diagram, in which at very long times there are no switch, at very short times you have the minimum number of pulses required for that given voltage, which in this case is 3, and then you increase the time, you need more pulses until you see this thing diverges until beyond a certain threshold you don't see switching anymore. So this was our clean-cut prediction, and then Pablo Stolia, who was working with me, but is really originally an electronic engineer, went to NAM and prepared the experiment by himself and did the experiment. And this is the experimental results. Experimental results are 1, 2, 3, 4, and then in the 5th pulse, you see the very fast transition to the low resistance state, and you can do that systematically and see that this thing clearly behaves as our prediction, therefore validate the system. And why I said that this is neuromorphic behavior? Because this thing really behaves as the training of a neuron. Formally, it's like the integrate and fire. So it depends on this time, you integrate a perturbation, and then suddenly you fire when you reach a threshold. But more clearly is the way you teach a child. So you have a child, and every time he behaves bad, you may choose to scold him or not. If you don't scold him or scold him very rarely, of course your child will never learn. But if you're very systematic and every time he does something bad, you just punish him, in very short time, it will learn very fast, and then this is a neuromorphic.
It's not allowed anymore. It's not allowed.
You give a nice thing called.
You can do it to graduate school.
Okay, so this is the summary of the talk. So I introduced this family, and in particular the GTS system, which we investigated at length, both theoretically and experimentally, with these very hard experiments at pressure with this tiny single crystal, and we have this new textbook case of the Mott system. This is the new icing system for strong correlated effects. I showed that the electric field-driven Mott insulator showed very universal behavior with the threshold behavior. We've seen that in different systems, between 3 and G and NISSE beyond, besides this new compound. I also introduced a phenomenological model based on what we learned about the coexistence of solutions within DMFT that captures the qualitative behavior of the model. And finally, I show the thing which I think is the most exciting message that you take home, which is the new functionality of Mott insulators. So at the end of the day, it may be that strongly correlated systems, such as the cuprates, will not give us levitating trains. The CMR will not give us multi-terabyte hard disk, miniature disk. But at the end of the day, the strongly correlated systems, the Mott systems, may be used to develop a totally dramatically new electronic units that will enable these neuromorphic inspired applications, opening a whole new game in the area of electronics. So thank you very much.